we're going to be learning about hybrid orbitals. Now, hybrid orbitals are kind of a weird thing. The word hybrid, Mr. Sams was telling us about this movie just a minute ago. What's it called, Mr. Sams?
Napoleon Dynamite. I guarantee you every single one of our students has seen it. You're the only person in the room who hasn't seen the movie.
I'm an old guy, okay? And apparently in Napoleon Dynamite, there's this critter that is made called
It's a drawing of a critter.
Oh, it's only a drawing of a critter?
Yeah, it's called
I don't know
a liger.
A liger. Apparently it is a tiger and a lion mixed together. And apparently the animal is sterile. All right, I'm being very scientific. Apparently it's a funny movie, but I've missed it. But today we want to talk about hybrid orbitals, okay? Now to illustrate that, I have brought with me today some chemicals here. All right, I have 3 chemicals. It's actually just colored water, but I have actually 4 beakers and 2 chemicals. I have over here a blue colored water, and then I've got orange, orange, and orange. Now, an orbital, if you recall, there are s orbitals, there are p orbitals, there are d and f orbitals. And so my analogy here is that the blue over here represents an s orbital, and the oranges represent a p orbital. So like 2s and 2p. Now, when orbitals are hybridized, they get all mixed up. So let me illustrate that by pouring them into my large flask. I'm going to pour all of my chemicals into the large flask. Remember, each of these containers represents an orbital. But when they become a bonding orbital, which we'll talk about in a minute, they become one continuous orbital. Instead of having one separate s orbital and 3 separate p orbitals, we have 4 orbitals that are all the same, and we call them sp3 orbitals. And they're all the same. And as you see, we've now made it purple. It was blue and orange, and now we've made the combination of purple. So let's see if we can see how that works with our lesson today. So today we're going to do hybrid orbitals, and this is podcast 9.1 in our lessons, and I'm trying to get my pen. Hybridization and the localized electron model. We're actually now, by the way, in chapter 9. So we have now moved out of chapter 8, and now we're in hybrid 9. So let's kind of talk ourselves through this. All right, what is hybridization?
Well, you just kind of showed us. It's when you take 2 things and kind of smush them together into something that has properties of both.
Yeah, so you kind of get a mixture of things, okay? All right, and now hybrid orbitals, and what we can illustrate that is I had an s orbital, let's say a 2s orbital, and then I have 3 2p orbitals. And I bet you can hear us better now. The mic's in the way. And what happens is they convert to one orbital that is now 4 orbitals. And this is called the sp3 orbital. These are all the same, where these are different. You see, these orbitals here are actually called atomic orbitals because they relate to atoms. And these are called molecular orbitals because they are now related to molecules. Molecules, molecular, atomic.
Hence the name.
Yeah, so hopefully that kind of makes some sense to you there, okay? All right. And then we've already talked about that, so that's important. Now let me give you an analogy. I'm not sure, Sam, you've seen this, but many people know that there are things such as roses. In fact, it's Valentine's Day this week.
It is.
Here, where at least you may be watching this, totally non-Valentine's Day. But it's Valentine's Day. And you know there are red roses.
Yes.
And there are yellow roses. But you know that if you were a really good rose person, a gardener or horticulturalist or whatever you call it, do you know that you could take that rose while it's growing and you could cut a piece out of it? I think a different color would be better here, huh? You could cut a little piece out of that rose. That really worked. And you could graft this yellow rose into this while this rose is growing. Now this rose, of course, has been cut. And then if you were to literally tape it together over time, you know what would happen to this rose?
Well, what's going to happen?
It would turn into a peach-colored rose. And they call those roses hybrid roses. So they actually hybridize roses, just kind of like we did with the colored water just a few minutes ago. You can hybridize roses. So all you got to do is graft one in. And so all the new flavors, or that's probably not the right word, but all the new colors and varieties, that's the word I'm looking for, of roses, many of them have been hybridized, and they're called hybrid orbitals, or not orbitals, hybrid roses. Okay? So let's take a look at this from more of a pictorial perspective. This is actually the picture that I was attempting to draw. Here I have atomic orbitals right here. Kind of here. So let's take
one S and 3 Ps.
So one S and 3 Ps, and when you pour them all together, so to speak, you make 4 orbitals that are called sp3 orbitals. All right? And the sp3 orbitals are the 4 purple orbitals, and they actually have different shapes too. We didn't really get into that, but this is the spherical shape, and these are of course our classic P shapes. But the sp3 orbitals they look like this. And then when you smush them together, they look like this.
Hey, it looks kind of tetrahedral to me.
Yeah, it is the form of a tetrahedron.
Interesting.
And that's kind of the whole idea. Okay, now and then here is another picture of this. Here is the 3 2p orbitals, and then the 2s, and then they become sp3. And actually, from an energetic perspective, here's the s orbital, here are the p orbitals, and the sp3 is a little bit less than the p's.
And they're all equal.
And they're all equal.
Yeah.
That's important. And this is what it would look like, again, with the CH4 molecule, and it is the corners of a tetrahedron, because there are 4 shapes, so it makes the tetrahedral shape. And this would still be sp3 orbital, and you can see a lone pair. This, if you can't really tell, this is ammonia NH3.
Yeah, that's one of those shapes that's derived from the tetrahedral shape.
Right, remember
it pyramidal.
The pyramidal shape. We
pyramidal.
Talked about pyramidal. All right. Now, we can also have, this is actually just let me back up and say, this is essentially a 4-cloud model right here.
Yeah.
So we call that sp3. Okay? Now, if I have a 3-cloud model, you've got an s orbital, and you've got 2 p orbitals. Now, I know there's a 3rd p orbital, but it's going to do something else we'll learn about in a little bit.
It's not actually going to hybridize and bond. It's just going to hang out.
It stays as an atomic orbital, actually.
Yeah.
And so if you take an s and then 2 of the p orbitals, and you smoosh them together, you get 3 new ones, 3 green ones, at least in the color scheme we have going on here, and then they take the shape of a
trigonal planar.
Trigonal planar. That's just the 3-cloud model, right? And we call this sp2 hybridized. And notice we have the 3 2p orbitals, which we talked about, and the 2s orbitals, and they turn into 3 sp2 orbitals, and then the 2p orbital does not change.
Nope.
All right? And then you can see a picture of that.
Yeah.
Actually, this is a pretty good picture. I like this picture. As you can see right here, here, and here, that is the sp2 orbital.
And notice they are all in the single plane.
They're in the plane.
Planar.
And then the blue here is the p orbital.
Right. It's the unhybridized atomic orbital.
Yes, exactly. And then when you have 2 sp2 orbitals getting together, it would look something like this, and the electrons are shared in these particular orbitals. This would be
C2H4.
C2H4, yeah. And there's something else going on there which we'll learn about later.
Yeah.
Now that leads us to 2 important definitions. They're actually in a covalent bond. There are actually 2 varieties of covalent bonds. Now we've talked about single, double, and triple, but at another level there's what we call sigma bonds. Now a sigma bond is a bond that is what's called an overlapping orbital bond.
Yep, and that's what occurs in a single bond.
So if we go back to this orbital picture right here, these 2 orbitals, this one right here and this one right here, are overlapping. So this is called a sigma bond. Now in a sigma bond, by the way, the symbol is the Greek letter sigma. This also would be a sigma bond. Now actually a side note here, this is sp2 hybridized, and this is an s atomic orbital, because this is just hydrogen with an atom.
Yeah.
So that is also a sigma bond. So in the picture I see 5 sigma bonds right there.
That's a very good AP question. How many sigma bonds and how many pi bonds are in the following compound?
So let's take a look at a pi bond. Pi bonds are non-overlapping bonds. This is the weird one, and of course it uses the symbol pi, like in mathematics. All right, now here's the thing that's odd here. So if I have a p orbital, okay, this is a p orbital.
Right, that's an unhybridized atomic orbital there.
And this is another one. And here's the odd thing. The electrons between this orbital and this orbital, they share. but they don't touch. Non-overlapping. Hence the dashed line and the electrons here. Are the electrons ever in between there?
No.
No. But somehow there is some connection between this orbital and this orbital, even though it's like the force field. I mean, I don't quite understand it, frankly.
And the interesting thing is that it could be in the top ones or the bottom ones, but together, those make one pi bond with 2 electrons total.
Yeah, there's just one electron in each of these. We don't know if they're sometimes they're on the top and sometimes in the bottom, and somehow they share and make a bond. That is called a pi bond. All right, so now if we take a more complex, this is that C2H4. Here's the molecule right here, written in Lewis dot structure form. There are no extra electrons. And you can see the overlapping sigma bond between the C, but then this is the pi bond right here. So it turns out, how many pi bonds would this have, Mr. Sims?
One pi bond.
One pi bond.
If you have a single bond, you're looking at 1 sigma bond. If you have a double bond, you have 1 sigma bond and 1 pi bond.
So if I have like a weird compound, let's say I have C, N, and then I would need an extra H here, and I need an extra H here, and an H, and an H, and an H. Everybody copy this down for me, if you would. This would actually have 2 more electrons out to complete the Lewis structure. How many sigma bonds do I have in that, Mr. Sanders?
All right, well, let's count our single bonds first.
Let me change colors. That might be easier. Okay, so this would be 1, 2, 3, 4, that makes like a double. 4, 5, 6, 7, 8,
and
9.
1 of the triple is 9, so 9 sigma.
9 sigma bonds. And the pi bonds, I would have 1 there. And now, we haven't really talked about triple bonds. We'll do that in a minute, but that's 2, and actually the third part of the triple is also 1. So there are 3 pi bonds. Very AP question. How many sigma and how many pi bonds in a particular structure? Very, very common. All right. Now, what if you have 2 clouds? In this case, you'll have an s orbital and a p orbital, and they'll smoosh together, and they make the yellow, the hybrid orbital called, now this is called sp. By the way, you realize this is s and this is p, so it's sp. If there's spp, then it's sp2. It's sppp, sp3. Okay? PPP. That's what your little kids say, right?
I have a 3-year-old. He's obsessed.
Yeah, okay. So you get the idea. This right here, if this carbon is sp hybridized, meaning it has 2 clouds, then he's going to have an overlapping orbital right here. And it's going to be the yellow, and this bond angle is 180 degrees, and that's what we've learned about 2 clouds. All right, so if you look at the picture here, we've got the S, and then basically one of these gets smooshed together, and that becomes the 2 sp ones. And then we still have the 2 p orbitals, this guy and this guy, and they don't change at all. Okay, now if we want to look for a really cool picture, actually it's this one I want to look at, right? Yeah. This is carbon dioxide. Now, carbon dioxide is an interesting compound in that if you see right here, we have the yellow right here.
That's the hybridized sp.
Yeah, that's the sp orbital, and then we have the 2 atomic orbitals. This p orbital right here, okay, is interacting in that non-overlapping fashion with this orbital, and then this p orbital in the sort of x-plane, if you will, the y-plane, pardon me, and the y-plane is interacting with this one, making this bond. It's as if these electrons are shared in some fashion, though they don't touch. So how many sigma and pi bonds would we have in carbon dioxide, Mr. Sanders?
Oh, we're going to have 2 sigma bonds, 1 for each of the doubles, and then 2 pi bonds.
Right, because the first bond...
You wrote sigma twice.
Oh, you're right. So this I should have written pi. That's what I meant to do. All right. Now, there's also another interesting case where you can have 5 clouds. What happens when you have 5 clouds? And by the way, actually, why don't you guys get out your shape paper, and you'll notice that in the first column in your shape paper, if you'll notice something on our chart here, it's got the sp. So if you've got 2 clouds, it's called sp hybridization. If it's got 3 clouds, it's sp2, 4 clouds, sp3, 5 clouds, sp3d. By the way, sometimes sp3d is called dsp3. Same thing. And then sometimes, it's a little typo on my part, but it's sp3d2 if you have 6 clouds, or also d2sp3. All right?
And the nice thing is, if you add up all the exponents, assuming the s has a 1 exponent, they always add up to the number of clouds.
That's correct. So if you've got 5 clouds, it is called dsp3, and in the dsp3 you take the sides of a trigonal bipyramidal shape. Right? We've learned about this in the shaping deal. Mm-hmm. And if you get d2sp3, this is that octahedral shape, and that's how that works. Okay? And this picture kind of illustrates the rest of it. That looks like we're just
that was
about
a short one.
Can you imagine? We actually made a short podcast.
I know, it's great. Should we just stand here and chat for a while and
just
make
make
it nice
it longer
and long?
for them?
Yeah, probably should. So what are you doing this weekend? Do anything nice for your wife? Valentine's Day.
We're going to like a movie.
Oh, nice. Yeah, we're gonna do dinner.
Yeah.
And,
We got a movie.
We have
planned.
kids. Babysitters are too expensive.
Well, my kids are going to be the babysitters. Our church is having like a movie night for the adults, but my kids are the babysitters for the parents who are like little kids, like your age.
Oh, that's cool.
Yeah. Okay.
Did we bore you yet?
Okay, so now you know.
Bye, guys.
The exciting life of chemistry teachers on Valentine's Day. Woo! Rock and roll. Bye.